we start looking at getting into graphing polynomial functions, and in this video we emphasize just the end behavior of a polynomial function. And we'll start by recalling the graphs of these very basic polynomial functions. Let me throw the word polynomial in there so you understand that these do relate to what we're learning here when we're trying to graph polynomial functions. Let's start with y equals x squared. When you graph y equals x squared, if you plug in 0 for x, y is 0 squared, so you get the ordered pair 0, 0. If you plug in 1 for x, y is 1 squared, which is 1, so you get the ordered pair 1, 1. If x is negative 1, so you plug in negative 1 for x, y is negative 1 squared, which is also positive 1, so you get the ordered pair negative 1, positive 1. And let's say you plug in 3 for x, then y would be 3 squared, which is 9, so we get the ordered pair 3, 9, which is up here. And if you square negative 3, you also get positive 9, which is up here. So the graph of y equals x squared basically looks something like this, called a parabola. And the point is, the left and the right side of this graph both go up, because if you take a positive x value and square it, you'll get a positive number. If you take a negative x value and square it, you'll get a positive number. Okay, so both ends, both left and right ends of this graph go up. Conversely, if you look at y equals x cubed and plug in 0 for x, then y is 0 cubed, so you also get the ordered pair 0, 0. Plug in 1 for x, then y is 1 cubed, which is 1, so you get the ordered pair 1, 1. Plug in 2 for x, then y would be 2 cubed, which is 8. So if x is 2, y is 8. So the right side of the x cubed function also looks very similar to the x squared function, just a little steeper. But the difference is the left side. If you plug in negative 1 for x, then y is negative 1 to the third power, which is negative 1. So we get the ordered pair negative 1, negative 1. If you plug in negative 2 for x, negative 2 to the third power is negative 8. So y is negative 8. So the left side of this graph goes down. So on the right side, the graph goes up, because if you take a positive number and raise it to the third power, you get a positive. On the left, if you take a negative number and raise it to the third power, you get a negative. So the right end goes up, but the left end goes down. And in fact, let's summarize this. If x is raised to an even power, doesn't have to be the squared power, then if we plug in positive or negative numbers, we get a positive outcome, right? If you plug in a negative number to square, you get a positive. If you plug in a positive number to square, you also get a positive. Okay? But if x is raised to an odd power, then if we plug in a positive number, we get a positive outcome. If we plug in a negative number, we get a negative outcome. Okay, so we'll say this once again. So if I have y equals x to an even power, then I know on the left side of my graph I'm going to get positive y values, and on the right side of my graph I'll get positive y values as well, because a negative to an even is power, or is positive, and a positive number to an even is positive. If I have y equals x to an odd power, then if I plug in negatives, I get negative y values. If I plug in positives, I get positive y values. Okay, and so you can see these are called the ends of my graph, the left and right end. Above, we have shown the end behavior, or the left and right ends of these graphs. Okay, so that's pretty simple to follow. Let me modify this slightly now. Let's shrink this down so I can fit a couple more there. If I have y equals a negative number times x to the even power, then all that negative does, this negative flips my graph over. So now I get negative y values on each end. Or over here, if I have a negative times x to an odd power, it flips my graph over. And on the left, my graph goes up, and on the right, my graph goes down. So negatives have the effect, just like with transformations, the negative coefficient flips the graph over the x-axis. Okay? Alright, so those are end behaviors of polynomial functions. So let's get down to business here. When we talk about end behavior, we mean the extreme left and the extreme right sides of our graph. Okay? So what types of x values are we dealing with? If I'm going to the extreme right, I'm dealing with really big x values. So we're dealing with really big x values. On the right side, those x values are positive. If I go far to the left, I've still got really big x values, but they're negative. So I've got really big positive and negative x values, okay? So that's what we're talking about when we're dealing with end behavior, the extreme right and left sides of our graph. So let's do an example. Draw the ends of the graph only. So if I've got f of x equals 2x to the fifth plus 5x to the fourth minus 9x cubed plus x minus 10, what we need to understand is if I plug in, if I were to plug in huge x values, positive or negative, it doesn't matter, the highest, or let's say the leading term, which is the highest degreed term, dominates. Every other term is insignificant. Okay? Insignificant. There we go. So in this case, what I mean is this term dominates. That's my leading term, my highest degree term. These terms are insignificant. That's because, think about a really big x value, like 100 million. 100 million to the fifth power is so much bigger than 100 million to the fourth power, or 100 million to the third power. It dominates all these other terms, so we don't care about those. So what's the conclusion here? The leading term dictates our end behavior, because the end behavior is when you're dealing with the extreme x values. Okay? So the end behavior of this graph, the ends or end behavior, look like this. They behave like y equals 2x to the fifth. Okay? And the other stuff doesn't matter because it's when you're dealing with x values, these other things are insignificant. And all this is the same thing as x to the fifth, because a positive does not flip it over. Okay? And since this is an odd power, I know the right side of my graph is going to go up and the left side of my graph is going to go down. So that's my end behavior. Sometimes books will not write the axes, so it could be written as the left end curving down and the right end curving up like this, with no connection in the middle. So either way, that is the end behavior of this function dictated by the leading term. So that's our answer. Those are the ends of our graph. Let's do another example. First note, end behavior is dictated by the leading term. The leading term is easiest to identify if the polynomial is simplified, not factored. Okay? So here's the next example. This polynomial is factored, not simplified. So what we have to do is multiply all of this out to see what our leading term is. Multiply out to get the leading term. Now luckily, since we're only interested in the leading term, we don't really have to multiply everything out. So if I were to multiply this out, it would look like this. I have negative 2 times x squared. And if I multiplied x minus 3 to the fourth out, that would give me x to the fourth plus some other stuff that I don't care about, times x plus that 1 I also don't care about. I just want the first term of each. Right? If I multiply x minus 3 by itself 4 times, the first term is going to be x to the fourth. So now I've got to multiply these things. So I've got negative 2 times x squared times x to the fourth, because that's my first term, times x, and then I'll have smaller terms after that that are added. Negative 2 times x squared times x to the fourth is negative 2x to the sixth, times x is negative 2x to the seventh, plus smaller degree terms. And so now this is my leading term. And I know my end behavior is going to be y equals negative 2 x to the seventh. And since now I've got a negative times x to the seventh, so if I were to have a positive times x to the seventh, then my left end would go down and my right end would go up, because 7 is an odd power. But I've got a negative times x to the seventh, which means that it's going to flip over and my left end is going to go up and my right end is going to go down. So those are the ends of this function, and again, to do that we had to think of the simplified form to see my leading term.